All right, here we go. All right, so welcome to our very last play posit of the year. Congratulations, you made it. So today we are going to use what we've learned about circuits, use what we've learned about induction to describe the transient and steady state behaviors. And as a reminder, that's kind of t equals 0 right when we do something, and t equals a long time. Behavior of RL, sometimes called LR, LC, and RLC circuits. So we're going to start off by reminding us about Ampere's law for a solenoid. I know Ampere's law is a little bit of a weak spot in our instruction this year, but we will remind ourselves of it. And I've misspelled solenoid. Solenoid. Then we'll talk about what's an inductor in the context of a circuit, talk about how it's kind of the mirror image of a capacitor, do a little bit of differential equations to wrap things up. All right. So just as a reminder, here is a solenoid. As you can see, it is a multiple loops of wire, loops on loops of wire. And we have here in purple the displayed direction of the current. Now, you might remember for loops and solenoids, we have our version of the right-hand rule that tells us if we curl our fingers with the current, as we can do here, so out of the page on the top, into the page on the bottom, we end up with the direction of the magnetic field in the middle. This is just like what we did for our loops for induction, because that's what you do for loops. So we have our solenoid here, and we want to apply Ampere's law here. And as a reminder, Ampere's law is a little bit different. Instead of a flux integral, Ampere's law is a line integral. So it's the amount of field that is parallel to our curve, parallel to our Amperean loop. So in this case, you'll notice for most of this little loop that we've drawn, out here, there's just no field. Here, there is a field, but it's perpendicular to the loop, so it does not contribute to our line integral. Same for this side. So the only side that matters here is this side immersed in the field. So we can write that that's a B times the length of the loop, BL, equals, well, how much current is enclosed? Well, in this case, we've got quite a lot of current enclosed. We have, in this case, we have 1, 2, 3, 4, 5, but we've got some number n of turns that we have enclosed, and we actually get to count all of that current. So what we find in the end is that our magnetic field inside is mu0 times I times n over L, and sometimes this is written this way instead, mu0 I times, sometimes I've seen it called little n and called nu, where this is basically the turns per meter, so like what's the density of turns. So it's important to remember that little thing. So that's the magnetic field of a solenoid. Well, we're going to talk about solenoids again, these coils of wire, because they turn out to have a very useful property in circuits. So when we talk about an inductor in a circuit, what we always mean is a solenoid is some kind of loop of wire. And you can actually see that from the circuit symbol for a solenoid, which looks like a coil of wire, which looks like, the circuit symbol for an inductor, which looks like a solenoid. What does an inductor do? It stores magnetic energy, kind of like a capacitor, but a capacitor stores electric energy. It stores magnetic energy, and it also has another interesting property that it resists change. So kind of like we've been talking about with EM induction, these inductors, these coils, do not like changes. We define this thing about a solenoid. We define this quantity called the inductance, which is the ratio of the magnetic flux to the current. So how much flux do I get out with respect to the current that I put in? Well, I happen to know that my magnetic field through this is going to be mu0 times n, mu0 times n times I over length. So if I divide it by I, my I goes away. I am doing flux, so I have to multiply by area. And then because a solenoid typically has multiple loops, it has n loops, we multiply by n a second time. So our n actually gets squared here when we're talking about the inductance of solenoid. And that's because our flux gets multiplied by multiple loops. We actually, in a sense, have extra flux going through our thing. The unit of inductance here is called the Henry, which is a Weber per amp, or a Tesla meter squared per amp. Henry's for inductance. So what do these things do in a circuit? So let's imagine here in this case. So here I've got an inductor coil, and I'm sending some current through it. And let's just be very specific. We've got our current coming up the page, and then in this coil, it kind of dives down into the page, comes back out of the page, dives into the page, comes back out of the page. This is our little coil. And so if we set up our right hand that way, we can see, yes, in fact, we get this blue magnetic field to the left. So what happens in this inductor coil? Well, as long as our current is steady, as long as our B field is steady, as long as our current doesn't change, the inductor is happy. The inductor behaves like it's not there. It basically doesn't do anything. So kind of like with capacitors where I talked about the big air quotes resistance, if nothing's changing, the R, the amount of resistance offered by this inductor coil, it's not really resistance, is nothing. It's happy. It doesn't do anything. What happens, though, if I try to increase my current? Well, if I try to increase my current, let's see, my flux initially was to the left. If I try to increase my current, what's going to happen? Well, I'm going to even get more flux to the left. My magnetic field is going to get stronger and stronger and stronger. And Lenz's law, remember, here's a little loop of wire. The flux is changing. It says, oh, no, I don't like that. So which way does it try to induce a field? It tries to induce a field to the right. It tries to induce a backwards field. So it fights this change. And the way that this manifests in the circuit, is you actually get what's called a back EMF. I'm just going to write that back EMF. You get a voltage across the inductor, which is opposite to the flow of current. It tries to reduce the flow of current. The inductor tries to push back against the battery if this happens. So you actually get this back EMF. If you try to change the current, and thereby change the magnetic field, the inductor will try to stop you from changing the current. It'll try to reduce the current. We can actually figure out this voltage exactly if we remember that our flux is equal to L times I. That's how we defined our inductance L. Our electric potential, our EMF from Faraday's law, is the negative derivative of our magnetic flux because it's trying to fight that change. And as a result, we can put these together and find that the EMF, the voltage across my inductor, ends up being minus L times the derivative of current. And this is actually on your equation sheet. So this is a key equation for inductors. This is a key one. That the voltage across them is equal to the negative L times the derivative of current. And it is negative because it tries to fight you. So the faster you try to change a current, the harder and harder the solenoid, the inductor pushes back. So again, just to think about this a little bit, as we go across a resistor only ever uses up current. Its delta V is always negative if you're moving in the direction of the current. A solenoid, an inductor, on the other hand, can go either way. It can have a decreasing potential or an increasing potential. So as you go across an inductor, think about this minus sign. The potential is going to decrease if the current is increasing, and the potential is going to increase if the current is decreasing. So it's going to try to always do the opposite of what you want to do. It's always going to try to do the opposite of what you want to do. If you're trying to increase the current, it's going to give you less potential. If you're trying to decrease the current, it's going to give you more potential and push more through. They do store energy. And so the energy stored in an inductor is here. Hey, look, energy, it's a 1/2 something something squared. Here's our 1/2 Li squared for the energy of an inductor. So that's another key one, and that's on your equation sheet also. So when we start to put these in circuits, we know that they fight change, but let's talk a little bit philosophically about how to think about this. This is a really interesting perspective that I want to share with you. So there's mechanical analogs to what's going on in a circuit. You can think of a capacitor as a spring. So if I have something attached to a spring, and at first that spring is not stretched at all. When you first push on it, if you first try to stretch out a spring, it's going to pull back, but its force is proportional to how much you've stretched it. So at first, if you haven't stretched it at all, it applies no force. So this is kind of like an uncharged capacitor. If a capacitor is not charged, it doesn't push back against you when you start to push current through it. Remember how we said a capacitor kind of has no resistance when it's empty? Similar thing, a spring has no resistance if it's not stretched. As I push on it more and more and more, though, what happens, it stretches out and starts to push back further and further. And there's going to be some point, if I'm applying a fixed force F, there's going to be some point when I can't push it anymore. When the spring force and my applied force are going to be perfectly balanced, and I'm not going to be able to push it anymore. And this is analogous to a capacitor being fully charged. So capacitors, in a sense, behave like springs. And then, obviously, think about those RC circuits. If I let this go, my spring's going to discharge and release all that energy. So capacitors are a little bit like springs. In this metaphor, inductors are kind of like masses. Masses have inertia. They resist change. If I'm not trying to change anything about a mass, right? Think about Newton's first law. If a mass is just sitting there and I don't apply any forces to it, it doesn't change its motion. If I have it moving with some constant velocity, if it's already doing its thing, as long as I don't try to change it, nothing is bad. As long as I don't try to change it, it doesn't try to fight me. What if I try to apply a force to it? If I apply a force to it, well, at first, let's say it's at rest and I apply a force to it. At first, when I applied a force to it, the very first moment, its velocity is still 0. It doesn't respond right away. But then, as I apply that force over time, it starts to move. It eventually starts to move, and it will reach some velocity as I push it. So an inductor stops you from changing, and then if I want to slow it down, at first it takes some time for it to slow down. So inductors are kind of like masses. They resist change. They have like inertia in a circuit. You might be asking what a resistor is. Resistors are basically like friction. They're like drag. The faster you try to push current through them, the more energy they take from you. And so we have this kind of mechanical analogy for what's going on, that capacitors are like springs, inductors are like masses, and resistors slow the whole system down. And this is kind of one of those reasons why you think about those RC circuits, right? If a capacitor is a spring, you might expect if I let a capacitor go on its own that it would like bounce like a spring. Well, if I let a spring go with friction, with sufficient friction, it's just going to go and slowly stop. It's not going to bounce back and forth. All right. So you don't necessarily need that perspective, but it is helpful. So whenever I'm thinking about inductors, when I say that inductors are the mirror image of capacitors, here's what I mean by that. We talked a little bit with capacitors about these transient versus steady state conditions, right? We said that for a charging capacitor, like an empty capacitor behaves kind of like it's not there, and a charged capacitor blocks current through it. An inductor is the mirror image. When you first try to start changing things with an inductor, it refuses to let you change. So if you like close this switch here, if I come here and I close this switch, at first, you might think I'm going to get some current through my circuit, but my inductor is going to resist that change. At first, I'm going to get nothing. But if I wait long enough, I can kind of override the inductor, and it will eventually get used to things happening. And over time, if I wait long enough, it will stop fighting. It will end up with an effective kind of resistance of 0. So for my capacitor, remember, my current, so if I'm charging a capacitor, and we kind of saw this, if I'm charging a capacitor, my current is going to start out high and then decay to 0 as that capacitor gets more and more charged. In this case, my current is going to start out at 0 because my inductor is not going to let anything happen. My current's going to start out at 0, and then eventually over time, it'll come up. And in fact, this is an exponential curve, and I will prove some of that in a moment. So again, energy. capacitors store electrical energy, inductors store magnetic energy. So let's talk a little bit about one of the most important types of circuits, which is an LC circuit. So LC because it has an inductor and a capacitor. So let's say I charge up my capacitor, positive side, negative side, and then I try to connect it to an inductor. So at some point I start my experiment and I close this switch. Well, just like in our RC circuit lab, our capacitor is going to try to discharge. That charge is going to try to drain away, and we're going to end up with some current flowing through our circuit. But remember, the inductor doesn't love that. It doesn't really want current flowing through our circuit. So at first it's going to resist a whole lot. And then what happens after that? Well, we're not entirely sure. We got to think about this a little bit. So let's take a look at, we're going to do this through differential equations and our loop law. So let's imagine that we've started this up and we've got some current going this way. And we're going to use our Kirchhoff's loop law, and we're going to go around this way. So let's go ahead and take a look at that. Well, the voltage that I get going across my capacitor, well, I'm going in the positive direction. So I'm going to get a Q over C here. As I go across my inductor, I'm going to get, well, for an inductor, I happen to know it's minus L di dt. And those are the only two things in my circuit. So I can rearrange this a little bit. I'm going to rewrite it this way. Di dt equals Q over LC. All right. Now, the thing is, what is this current doing? This current is reducing the charge on my capacitor. So I can actually write that I is negative dq dt. So because as my current flows, my capacitor is discharging, the charge is going down and down and down and down. So if I substitute that in, let's see, I have to take a derivative of that. So let's see, I'm going to end up with negative second derivative of Q equals Q over LC. Let's just push the minus sign to the other side here. I feel like I've seen something like this somewhere before, where the second derivative of something is equal to minus, oh, great announcements. That's going to be in my play posits forever. I feel like I've seen something like this before. Where the second derivative of something is equal to the negative of the original function. And if you're looking at this and saying, aha, I remember that from mechanics, this is simple harmonic motion. And it is simple harmonic motion with an omega equal to 1 over root LC. This is simple harmonic motion, but you might be saying, Mr. Bates, that's crazy. What's moving? This is not a physical thing. It's not a spring. There's nothing going back and forth. What's going back and forth? What is moving like a sine wave in this case? And the answer is, in this equation, it's the charge that's moving back and forth like a sine wave. So if I look at my capacitor charge over time, it's going to move, I guess, actually like a cosine wave because it's going to start out fully charged. It's going to oscillate back and forth. And the current will be the negative derivative of that and will move like a sine wave. So when my capacitor is fully charged at the very first moment, I get no current. After some time goes by, my inductor kind of relaxes and lets some current happen. And we'll kind of go through each phase of this, but this is an electric oscillator. It is simple harmonic motion, but it's charge and current that are oscillating. And so we find that it oscillates and it has this frequency, root 1 over LC. They expect you to know this, but they don't give it to you. So just like for RC circuits, right? Tau for an RC circuit was just literally R times C, the time constant there. They expect you to know that omega is root 1 over LC for this. So what the heck is sloshing back and forth? How can we interpret this? Well, let's start at this first moment when everything is charged just when we close the switch. This is like having a fully stretched spring. The moment we let it go, there's no velocity yet because we've just let it go. It's literally the first moment. It's just starting to move. Nothing's happened yet. So we have no velocity. We have no velocity, we have no current. So in this, so our current starts off at 0. Now, as that spring starts to move, you get some current going through our system. And again, over time, inductors try to fight change, but like most things, they can't fight it forever. So eventually they kind of like get used to it. And our current starts to rise. And what happens over time is that the charge on our capacitor runs out. And when the charge on our capacitor runs out, it's not pushing current as hard through our circuit, kind of like how there's not as much force on a spring that's at equilibrium. And so the current starts to level off. The current starts to level off. Well, you might think, well, if the capacitor is out of charge, current's going to stop. But remember, the inductor has now allowed a bunch of current to flow, and it doesn't like change. So it's going to keep that current moving, regardless of what anybody else thinks. It's going to keep that current moving. So just like the spring, it's got momentum to carry it through. The inductor has momentum and says, no, 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 no. You wanted current going this way through the circuit. You're going to get it. And the inductor actually holds on long enough to charge the capacitor the other way. It actually manages to, that kind of the positive charge overshoots and sloshes all the way around and reverses the polarity on the capacitor. And then it happens, the whole thing happens in reverse. It sloshes back. So what we end up with in the end is the inductor's fighting it, is okay with it. And now it's fighting to make sure that current keeps going. And now it's kind of fighting the change the other way. And what we end up with is that the inductor just kind of keeps things moving. It never wants to give up. It never wants to stop. It always wants to stop what's going on, but kind of keeps things sloshing back and forth. Because once the current starts going clockwise, it wants it to keep going clockwise. Once it starts going counterclockwise, it wants it to keep going counterclockwise. LC circuits are really important. Anything that oscillates, anything that needs to make a wave, which is most communication devices and things like that, have an LC circuit in there somewhere as an oscillator, because again, you can tune that frequency, right? If you know the frequency is given this way, you can tune it and you can pick your inductor and you can pick your capacitor such that you get exactly the frequency of oscillation that you want. And you can send signals and pick up signals and receive them and all kinds of things like that. So LC circuits are found absolutely everywhere. They are little harmonic oscillators of the electronics world. Last but not least, we want to talk a little bit about RL circuits. So this is a resistor and an inductor. And so you can imagine that we've had some current flowing through our circuit for a while. So our inductor has chilled out. There's some amount of current flowing through. And then let's say we try to shut it off. So we move the switch from A, connected to the battery, to B. So all of a sudden, we've cut the battery out. We try to turn off our system. So we've kind of cut out this side of the circuit. What happens to that? Well, current's been flowing through our circuit. Inductors do not like that to stop, so the current does not switch off right away. The inductor kind of takes over from the battery and tries to continue to drive the motion. So let's take a look at our differential equation for this. So let's do another differential equations investigation. In this case, if we follow our loop this way, I'm going to get, let's see, minus Ri, or minus IR, from Ohm's law over our resistor, minus L di dt over here equals 0. So if I go ahead and set that up, let's see, I end up with something that looks like this. That looks like di dt equals negative R over L times I. And you might say, oh, it's simple harmonic motion again, but be careful. This is only a first derivative on this side. So what we actually get is kind of like with our RC circuit, we get something where our current goes as e to the negative t over some constant tau. Let's actually just do this whole integral out. I know that it's, we don't want to take up too much time, but let's just do this. So we end up with di over I equals negative r over L dt. So in this case, we integrate the left side and we get, excuse me, we're going to integrate this from wherever we start, from I0 to, some later current I, because it's going down. And we're going to integrate this from time 0 to time t. So on the left side, we're going to get ln of I over I0 equals negative r over L t. And when we do e to that, we end up with something like this. And our tau in this case is given to us by L over R. So this is for an LR circuit. This is our new time constant. If we have a bigger inductor, it takes longer for our circuit to run out of current. If we have a bigger resistor, though, resistance is like drag. It takes us less time. So this is exponential. It looks just like a capacitor. It looks just like an RC circuit in a sense, that it slowly runs out of current. The inductor keeps it going as long as it possibly can, So it looks a lot like an RC circuit. Last but not least, sometimes they won't make you do these full out on the exam, although they will make you do this in college in differential equations. You can look at what's called an RLC circuit, which has all three of them. So it's like having a mass and a spring and friction. So the most typical behavior of this is that you get these, what's called the underdamped. You get these oscillations that just decay over time. If your resistor is really, really big, you can get these extra damped conditions where it basically oscillates once or not at all. It basically just goes to zero. Imagine, trying to do like a spring on sandpaper, right? It's not going to really bounce back and forth. It'll just kind of go and stop moving. They don't expect you to know how to do these mathematically, but they may expect you to know that if we stick a resistor in an LC circuit, that it'll decay over time. So let's take a look at one example. Here's an RL circuit. It's got a resistor and an inductor. And so we're going to keep this open for a long time, so there's no initial current. Our initial current is nothing. And then at time equals 0, we're going to close it. So the very first moment it asks us, what is the current in the circuit? It asks a different question. What is the current in the circuit after the switch has been closed? A long time. Well, at first, at t equals 0, the inductor isn't going to let any current through. But then, after a while, the inductor gets used to it, gives up the ghost, and our current will rise to some value. And the thing that I always like to remember is that an inductor gets used to things. So after a really long time, it has an effective resistance of nothing. It doesn't fight. So if it waits long enough, it behaves like it's not even there. And so what's our current? It's 12 divided by 6 gives us 2 amps. Then it asks us, what's the potential difference across the resistor immediately after the switch is closed? Well, immediately after the switch is closed, we're not going to get any current. The moment we close the switch, the inductor tries to keep the status quo as long as it can. The moment after we close the switch, it's not moving yet. It's not ready to let any current in yet. So this is kind of that R equals infinity case. The inductor is really not going to let anything through. So if there's no current at first, there's no current the moment we close the switch, well, what is the voltage drop across this resistor? Well, if our current's nothing, there's nothing across our resistor. So if you imagine that instead of a resistor, this was a light bulb, what would happen is the moment you close the switch, nothing would happen. The light bulb wouldn't come on. And then over a couple seconds, the light bulb would slowly fade into view. As a quick editorial note, this is actually a big problem in a lot of circuits because inductance builds up kind of naturally. Anytime you have wires and you have magnetic fields, you have some inductance. And what can happen sometimes is, let's say you're working on some high voltage circuit and you try to open a switch. What can happen is you try to open that switch to interrupt the circuit. And if there's enough inductance in your circuit, it can actually push a back EMF hard enough, it can build up enough voltage due to that sudden change in current. Because remember, the voltage it generates is proportional to the rate of change of current. So if you try to shut off the current really fast, you get a huge voltage. And so what can actually happen is you can end up with a spark. You try to open up the switch and the system will actually put a big spark across your switch as it opens up and like shock you as you're trying to undo it, because that's the inductance of your circuit saying, no, bad person, I don't want any change, don't open my switch. All right, we're going to look at this a little bit more in class, but a quick summary of this. Inductors kind of act like a mass. At first, they resist any change in current, any change in your circuit. So I like to think of that as transient changes. They don't let happen. They maintain the status quo at time equals 0. Over time, they basically act like they're not there. You give them long enough to get used to it, they basically go away. You pretend that they don't exist. And that's kind of the mirror image of capacitors. If you have an LC circuit, they oscillate with this frequency, with this angular frequency. And if you have an RL circuit, they're exponential, exponential rise, exponential decay with this time constant. All right, see you in class.